Studying advanced mathematics can be challenging enough without doing it in ancient dead languages. But for Dr. Clemency Montelle, that's just when the fun began. Hi Clemency, how are you?
Good, thank you.
Now, first off, which came first, the languages or the maths?
Well, actually, they both came at about the same time. I, as an undergraduate, had really no idea what I wanted to do for my degree. So I signed up for mathematics because I'd enjoyed it at school, and did Greek and Latin as well because it sounded like a good education. And I remember people saying, Clemency, what on earth are you going to do with your classical studies and your mathematics? What on earth do they have in common? And so it must have been about 4 years after starting this in my honours year, which I was browsing in the stacks looking for some ancient Greek text, and I came across the shelf and I saw a copy of Euclid in Greek, and I thought, hold on, this is mathematics in Greek. I can read this stuff. And so this was just the epiphany moment, and I suddenly thought, this is what I want to do. Read ancient mathematical texts in dead languages and try and figure out what they mean. So I started with the Greek, and then could read also texts in Latin, and then naturally for people who are studying Indo-European languages such as Greek and Latin, you go to Sanskrit, which is a very old form of modern-day Hindi, and Arabic, and lastly cuneiform, because all of these mathematical cultures were communicating with each other at some point in some stage.
Oh really, so you're like one of the first of your kind pioneering through this unique pulling together of...
Well, I mean there are other, plenty of other scholars who combine these rare skills, but they're far and few in society, and the path to getting there is often one that's very personal rather than, hey, let's do history of maths right from the very beginning.
So for you it's like the perfect bridge. You can bring two things together that you love doing.
Absolutely, absolutely.
Okay, so having realised that, what is it that you actually do?
So, very simply, I find ancient manuscripts or books, such as this one, this is Euclid's Elements, read it in the Greek or the Latin or the Sanskrit or the Arabic, try and figure out what the mathematics says, and say more general things about the mathematical culture.
Okay, because you think that we don't necessarily know exactly what they mean.
That's correct. Well, some of them haven't even been read in the modern time. So very ancient texts, when we want to say something about the mathematical culture and some of these very early cultures, we just have no idea because many sources remain unread. And it's because precisely you need this blend of not being afraid of the mathematics and also being able to read the languages that you can really adequately get a sense of what's going on.
So how much can get lost in translation?
Well, this is the interesting thing. A lot of people think that mathematics is sort of value-free, this kind of universal language. But in fact, looking at the history, we see that in fact mathematics is quite culturally sensitive. That is, different cultures have different ways of thinking about things and expressing things and doing mathematics in the end. So it not only is interesting from a historical sense in learning about our heritage and our past in various mathematical cultures, but also it helps clarify what we are doing in mathematics today.
Okay, so that's its sort of useful application,
right,
if you like. So
absolutely.
you clarify those sort of things, and are there also lots of texts that, because this book here, for instance, this is the original Greek stuff, isn't it?
This is correct. So this is, well...
That's my technical word, Greek stuff. It's very highly informed of me. Yeah.
Well, in fact, this is very late. So this is a book of Euclid's Elements.
Yep.
And Euclid was around, we're not sure quite when, but about 300 BCE.
Right.
So that's just over 2,000 years ago.
Right.
And originally, the Greek would have been written on various parchments or the like.
Papyrus and all that sort of carry
correct,
on.
yeah.
Yep.
And of course the manuscripts were copied by later generations and it's been handed down like that to us. So this book here is actually from the 1700s, which is quite old, we think, but relatively late for Euclid. And of course it's typeset with pictures.
So they would have, how have they written this book? They'd have gone back to those ancient things to write this?
That's right, yeah.
Okay, so there'd been some guy going, okay, well I can read that, and
that's right, and he will have, and sent it to the publisher who would have typeset it. Yep.
But we rely on how good he is, of course, don't we?
Absolutely.
This is where all the human links in the chain that can go wrong or right.
So in fact, the interesting question becomes, we have much earlier manuscripts, and you can take those and compare this and see what's happened and what's done. Probably, very few manuscripts are actually based on the original. You know, this is kind of this mysterious, you know, hypothetical text. So of course, every time something gets copied, it gets changed a little bit, or people make mistakes or leave out lines, or they might add bits because they think they know better.
Yes.
And so gradually as you go through time, all these manuscripts change slightly differently. So the tradition gets more and more complicated. So it's actually kind of projecting back into past to see actually what the real mathematics might have looked like.
So do you get to look at, I mean this is 1700s, but do you get to look at that real ancient stuff?
Absolutely.
You do?
I've been to the British Museum and held cuneiform tablets which are made out of clay, and I have a facsimile here.
Just happened to have prepared one earlier.
That's right.
Yes,
it is unfortunately not a mathematical text. I'd like to get my hands on that.
Okay.
It's a legal text, but just to give you an idea, you can see this is a tablet which is quite small and made out of clay, and it's been fired, so it's very durable, which is why we have artifacts that are almost 5,000 years in some cases. Of course, paper, as you can see, decays very quickly.
Yes.
Clay and pottery, especially when it's dug in the sand, which is generally dry and quite well preserving versus a very humid or wet environment, have lasted really well. So we can get ideas about the sort of intellectual activities these individuals were getting up to, including mathematics.
Are there any other applications from this?
Well, often you will find that active mathematicians, particularly in the purer fields who are thinking about more abstract mathematical relations, will read earlier texts and just be inspired and think about, gosh, what if he hadn't assumed this? What kind of mathematical system would result? And we have lots of wonderful instances in history where people have just slightly changed what the ancients have done, and they've given rise to huge new mathematical fields. For example, in Euclid's Elements, he starts up by giving all his definitions and axioms, and one of these is to do with his definition of parallel lines. He says parallel lines, you know, never meet at a point. In fact, the definition is a bit nuanced. He actually doesn't actually mention the word parallel lines, but 1,000 years later, or even you know, a millennia and a half later, some mathematicians came along and said, what say we have systems where parallel lines do meet? And it gave rise to this whole new field of mathematics called non-Euclidean geometries, where you're dealing with parallel lines, for example, on the sphere, lines of longitude and latitude. You can imagine they're parallel, but they do intersect up at the poles.
Yes.
So,
Okay.
So looking at very early mathematics can sometimes be hugely stimulating for mathematicians in modern day times.
Yes, okay, so they're looking right at that original stuff and they go, hold on a minute, what if that had happened? Bum, 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 bum.
Absolutely.
Okay, now the other thing is, what is your favourite part of this work that you do? Is it going back to that original stuff and a sort of a...
I think so. There's a wonderful sense of history and sort of this, the mystery behind it. I think, you know, you can get quite romantic because in fact it is just really hard work, you know. You know, you've got reading
like
every
archaeology,
single
it
word.
sounds great, but there they are chipping away at something for days.
It's very, very slow. But overall, just getting a sense of reading these ancient words and being able to understand them and getting a sense for this wonderful universality of mathematics as an intellectual pursuit that has been common to almost all cultures. Yeah.
So you're right there at the beginning when these people had these most amazing ideas,
Absolutely.
kind of out of the blue. I mean,
and trying to think about what inspired them and where these ideas went. So yes, that's just...
Very cool. Hey, like I also understand, I hear it on very good authority, that you can in fact chant in Sanskrit. Is that right? Is that true? That's what I understand.
Well, I mean, here's an interesting thing. Mathematics in India, for the longest time, was conducted in an oral environment. So they didn't write anything down. So everything that they wrote about, they would have to memorize and pass on from father to son, from teacher to student, orally. So they have wonderful techniques in order to make this stuff memorable, because you can imagine trying to fit theorems and propositions into sort of a metrical pattern, you know, hypotenuses and square roots and areas and cubes and addition and subtraction into a kind of poetic framework is quite difficult. It requires you to be a bit of a poet as well as a mathematician. And so you see interesting things happen to the mathematics in that case. You know, they'll chuck out their technical terminology, they use interesting, colourful words for numbers, just in the aid of making it memorable. And also what you see is you don't get any huge, big, long, compendious works like this, which are very carefully set out and proved with attention to detail. You get this wonderful brush stroke of mathematics that within sort of 30 lines, you've covered the whole entire mathematical field. Okay, and the idea is that it's supposed to be a memory jog. It's supposed to remind you of the broader details which you can fill in at the time. So for example, I won't use a mathematical example because, you know, the technology is bad, but for grammatical memorization, for example, we've got the word deva. They would chant something like to remind themselves of the different inflections of the verb, something like akarantaha punninga deva shabdaha. And there we go, deva, deva, devaha, edeva, edeva, edevaha, just to remind themselves of the different grammatical inflections of the word.
Nice. I think if math has been like that, I'd have done a lot better. Anyway, thank you very much for talking to us today, Clemency. It's been our pleasure.
You're very welcome.